Leachate is any liquid that in passing through matter, extracts solutes, suspended solids or any other component of the material through which it has passed. Leachate is a widely used term in the environmental sciences where it has the specific meaning of a liquid that has dissolved or entrained environmentally harmful substances which may then enter the environment. It is most commonly used in the context of landfilling of putrescible or industrial waste. In the narrow environmental context, leachate is therefore any liquid material that drains from land or stockpiled material and contains significantly elevated concentrations of undesirable material derived from the material that it has passed through. Landfill leachate. Leachate from a landfill varies widely in composition depending on the age of the landfill and the type of waste that it contains. It can usually contain both dissolved and suspended material. The generation of leachate is caused principally by precipitation percolating through waste deposited in a landfill. Once in contact with decomposing solid waste, the percolating water becomes contaminated, and if it then flows out of the waste material it is termed leachate. Additional leachate volume is produced during this decomposition of carbonaceous material, producing a wide range of other materials including methane, carbon dioxide and a complex mixture of organic acids, aldehydes, alcohols and simple sugars. The risks of leachate generation can be mitigated by properly designed and engineered landfill sites, such as sites that are constructed on geologically impermeable materials or sites that use impermeable liners made of geomembranes or engineered clay. The use of linings is now mandatory within both the United States and the European Union except where the waste is deemed inert. In addition, most toxic and difficult materials are now specifically excluded from landfilling. However, despite much stricter statutory controls, leachates from modern sites are found to contain a range of contaminants that may either be associated with some level of illegal activity or may reflect the ubiquitous use of a range of difficult materials in household and domestic products which enter the waste stream legally. Composition of landfill leachate. When water percolates through the waste, it promotes and assists the process of decomposition by bacteria and fungi. These processes in turn release byproducts of decomposition and rapidly use up any available oxygen, creating an anoxic environment. In actively decomposing waste, the temperature rises and the pH falls rapidly, and many metal ions which are relatively insoluble at neutral pH can become dissolved in the developing leachate. The decomposition processes themselves release further water which adds to the volume of leachate. Leachate also reacts with materials that are not themselves prone to decomposition such as fire ash, cement-based building materials and gypsum-based materials, changing the chemical composition. In sites with large volumes of building waste, especially those containing gypsum plaster, the reaction of leachate with the gypsum can generate large volumes of hydrogen sulfide which may be released in the leachate and may also form a large component of the landfill gas. In a landfill that receives a mixture of municipal, commercial, and mixed industrial waste, but excludes significant amounts of concentrated specific chemical waste, landfill leachate may be characterized as a water-based solution of 4 groups of contaminants. Dissolved organic matter, inorganic macrocomponents, heavy metals, and xenobiotic organic compounds such as halogenated organics. The physical appearance of leachate when it emerges from a typical landfill site is a strongly odored black, yellow or orange-colored cloudy liquid. The smell is acidic and offensive and may be very pervasive because of hydrogen, nitrogen and sulfur-rich organic species such as mercaptans. Leachate management. In older landfills and those with no membrane between the waste and the underlying geology, leachate is free to egress the waste directly into the groundwater. In such cases, high concentrations of leachate are often found in nearby springs and flushes. As leachate first emerges, it can be black in color, anoxic and may be effervescent with dissolved and entrained gases. As it becomes oxygenated, it tends to turn brown or yellow because of the presence of iron salts in solution and in suspension. It also quickly develops a bacterial flora often comprising substantial growths of Spherodilus. History of landfill leachate collection. In the UK, in the late 1960s, central government policy was to ensure new landfill sites were being chosen with permeable underlying geological strata to avoid the buildup of leachate. This policy was dubbed dilute and disperse. However, following a number of cases where this policy was seen to be failing and an expose in the Sunday Times of serious environmental damage being caused by inappropriate disposal of industrial wastes, both policy and the law was changed. The Deposit of Poisonous Wastes Act 1972 together with the 1974 Local Government Act, made local government responsible for waste disposal and also responsible for environmental standards enforcement for waste disposal. Proposed landfill locations also needed to be justified not only by geography but also scientifically. Many European countries decided to select sites in groundwater-free clay geological conditions or to seal each site with an engineered lining. In the wake of European advancements, the United States increased its development of leachate retaining and collection systems. This quickly led from lining in principle, into the use of multiple lining layers in all landfills. Goals of leachate collection systems. The primary criterion for design of the leachate system is that all leachate be collected and removed from the landfill at a rate sufficient to prevent an unacceptable hydraulic head occurring at any point over the lining system. Components of leachate collection systems. There are many components to a collection system including pumps, manholes, discharge lines and liquid level monitors. However, there are four main components which govern the overall efficiency of the system. These four elements are liners, filters, pumps and sumps. Liners, natural and synthetic liners may be utilized as both a collection device, and as a means for isolating leachate within the filter to protect the soil and groundwater below. The chief concern is a liner's ability to maintain integrity and impermeability over the life of the landfill. Subsurface water monitoring, leachate collection, and clay liners are commonly included in the design and construction of a waste landfill. To effectively serve the purpose of containing leachate in a landfill, a liner system must possess a number of physical properties. The liner must have high tensile strength, flexibility, and elongation without failure. It is also important that the liner resists abrasion, puncture, and chemical degradation by leachate. Lastly, the liner must withstand temperature variation, be black, easily installed, and economical. There are several types of liners used in leachate control and collection. These types include geomembranes, geosynthetic clay liners, geotextiles, geogrids, geonets, and geocomposites. Each style of liner has specific uses and abilities. Geomembranes are used to provide a barrier between mobile polluting substances released from wastes and the groundwater. In the closing of landfills, geomembranes are used to provide a low permeability cover barrier to prevent the intrusion of rainwater. Geosynthetic clay liners are fabricated by distributing sodium bentonite in a uniform thickness between woven and non-woven geotextiles. Sodium bentonite has a low permeability which makes GCLs a suitable alternative to clay liners in a composite liner system. Geotextiles are used as separation between two different types of soils to prevent contamination of the lower layer by the upper layer. Geotextiles also act as a cushion to protect synthetic layers against puncture from underlying and overlaying rocks. Geogrids are structural synthetic materials used in slope veneer stability to create stability for cover soils over synthetic liners or as soil reinforcement in steep slopes. Geonets are synthetic drainage materials which are often used in lieu of sand and gravel. RADs can take 12 inches of drainage sand, thus increasing the landfill space for waste. Geocomposites are a combination of synthetic materials ordinarily used singly. A common type of geocomposite is a geonet heat bonded to two layers of geotextile, one on each side. The geocomposite serves as a filter and drainage medium. Geosynthetic clay liners are a type of combination liner. One advantage to using a geosynthetic clay liner is the ability to order exact amounts of the liner. Ordering precise amounts from the manufacturer prevents surplus and overspending. Another advantage to GCLA Euro unregistered trademark S is the liner can serve appropriately in areas without an adequate clay source. Conversely, GCLA Euro unregistered trademark S are heavy, cumbersome, and installation is very labor-intensive. In addition to be arduous and difficult under normal conditions, Installation can be cancelled during damp conditions because the bentonite absorbs the water, making it even more burdensome and tedious. Leachate drainage system. The leachate drainage system is responsible for the collection and transport of the leachate collected inside the liner. The pipe dimensions, type, and layout must all be planned with the weight and pressure of waste and transport vehicles in mind. The pipes are located on the floor of the cell. Above the network lies an enormous amount of weight and pressure. To support this, the pipes can either be flexible or rigid. However, the joints to connect the pipes yield better results if the connections are flexible. An alternative to placing the collection system underneath the waste is to position the conduits in trenches or above grade. The collection pipe network of a leachate collection system drains, collects, and transports leachate through the drainage layer to a collection sump where it is removed for treatment or disposal. The pipes also serve as drains within the drainage layer to minimize the mounding of leachate in the layer. These pipes are designed with cuts which are inclined to 120 degrees, which prevents entry of solid particles in it. Filters. The filter layer is used above the drainage layer in leachate collection. There are two types of filters typically used in engineering practices: granular and geotextile. Granular filters consist of one or more soil layer or multiple layers having a coarser gradation in the direction of the seepage than the soil to be protected. Sumps or leachate well. As liquid enters the landfill cell, it moves down the filter, passes through the pipe network, and rests in the sump. As collection systems are planned, the number, location, and size of the sumps are vital to an efficient operation. When designing sumps, the amount of leachate and liquid expected is the foremost concern. Areas in which rainfall is higher than average typically have larger sumps. A further criterion for sump planning is accounting for the pump capacity. The relationship of pump capacity and sump size is inversed. If the pump capacity is low, the volume of the sump should be larger than average. It is critical for the volume of the sump to be able to store the expected leachate between pumping cycles. This relationship helps maintain a healthy operation. Some pumps can function with preset phase times. If the flow is not predictable, a predetermined leachate height level can automatically switch the system on. Other conditions for sump planning are maintenance and pump drawdown. Collection pipes typically convey the leachate by gravity to one or more sumps, depending upon the size of the area drained. Leachate collected in the sump is removed by pumping to a vehicle, to a holding facility for subsequent vehicle pickup, or to an on-site treatment facility. Sump dimensions are governed by the amount of leachate to be stored, pump capacity, and minimum pump drawdown. The volume of the sump must be sufficient to hold the maximum amount of leachate anticipated between pump cycles, plus an additional volume equal to the minimum pump drawdown volume. Sump size should also consider dimensional requirements for conducting maintenance and inspection activities. Some pumps may operate with preset cycling times or, if leachate flow is less predictable, the pump may be automatically switched on when the leachate reaches a predetermined level. Membrane and collection for treatment. More modern landfills in the developed world have some form of membrane separating the waste from the surrounding ground, and in such sites there is often a leachate collection series of pipes laid on the membrane to convey the leachate to a collection or treatment location. For an example of a treatment system with only minor membrane use, see Landfill landfill site. All membranes are porous to some limited extent so that over time low volumes of leachate will cross the membrane. The design of landfill membranes is at such low volumes that they should never have a measurable adverse impact on the quality of the receiving groundwater. A more significant risk may be the failure or abandonment of the leachate collection system. Such systems are prone to internal failure as landfills suffer large internal movements as waste decomposes unevenly and thus buckles and distorts pipes. If a leachate collection system fails, leachate levels will slowly build in a site and may even overtop the containing membrane and flow out into the environment. Rising leachate levels can also wet waste masses that have previously been dry, triggering further active decomposition and leachate generation. Thus what appears to be a stabilized and inactive site can become reactivated and restart significant gas production and exhibit significant changes in finished ground levels. Reinjection into landfill. One method of leachate management that was more common in uncontained sites was leachate recirculation, in which leachate was collected and re-injected into the waste mass. This process greatly accelerated decomposition and therefore gas production, and had the impact of converting some leachate volume into landfill gas and reducing the overall volume of leachate for disposal. However, it also tended to increase substantially the concentrations of contaminant materials, making it a more difficult waste to treat. Treatment. The most common method of handling collected leachate is on-site treatment. When treating leachate on-site, the leachate is pumped from the sump into the treatment tanks. The leachate may then be mixed with chemical reagents to modify the pH and to coagulate unsettled solids and to reduce the concentration of hazardous matter. Further treatment is typically a modified form of activated sludge to substantially reduce the dissolved organic content. Nutrient imbalance can cause difficulties in maintaining an effective biological treatment stage. The treated liquor is rarely of sufficient quality to be released to the environment and may be tankered or piped to a local sewage treatment facility. Of course, it depends how old is the landfill and what is the limit needed to achieve after treatment. With high conductivity leachate is hard to treat with biological treatment, and with chemical treatment. If the landfill is old and has high conductivity leachate, and it is need a precise treatment, you can treat with reverse osmosis RCDT modules technology. It has a high operation hours and you can recover up to 90% permeate. Of course, it is limited by conductivity and some inorganic elements present like C, bar, car, etc. Removal to sewer system. In some older landfills, leachate was directed to the sewers, but this can cause a number of problems. Toxic metals from leachate passing through the sewage treatment plant concentrate in the sewage sludge, making it difficult or dangerous to dispose of the sludge without incurring a risk to the environment. In Europe, regulations and controls have improved in recent decades and toxic wastes are now no longer permitted to be disposed of to the municipal solid waste landfills, and in most developed countries the metals problem has diminished. Paradoxically, however, as sewage treatment works discharges are being improved throughout Europe and many other countries, the sewage treatment works operators are finding that leachates are difficult waste streams to treat. This is because leachates contain very high ammoniacal nitrogen concentrations, they are usually very acidic, they are often anoxic and, if received in large volumes relative to the incoming sewage flow, they lack the phosphorus needed to prevent nutrient starvation for the biological communities that perform the sewage treatment processes. The result is that leachates are a difficult-to-treat waste stream. However, within aging municipal solid waste landfills, this may not be a problem as the pH returns close to neutral after the initial stage of acidogenic leachate decomposition. Many sewer undertakers limit maximum ammoniacal nitrogen concentration in their sewers to 250 mg per liter to protect sewer maintenance workers, as the WHO's maximum occupational safety limit would be exceeded at above penthouse 9 to 10, which is often the highest permitted pH of permitted sewer discharges. Many older leachate streams also contained a variety of synthetic organic species and their decomposition products, some of which have the potential to be acutely damaging to the environment. Environmental impact. The risks from waste leachate are due to its high organic contaminant concentrations and high concentration of ammonia. Pathogenic microorganisms that might be present in it are often cited as the most important, but pathogenic organism counts reduce rapidly with time in the landfill, so this only applies to the most fresh leachate. Toxic substances may however be present in variable concentration and their presence is related to the nature of waste deposited. Most landfills containing organic material will produce methane, some of which dissolves in the leachate. This could in theory be released in weakly ventilated areas in the treatment plant. All plants in Europe must now be assessed under the EU ATEX directive and zoned where explosion risks are identified to prevent future accidents. The most important requirement is the prevention of discharge of dissolved methane from untreated leachate when it is discharged into public sewers, and most sewage treatment authorities limit the permissible discharge concentration of dissolved methane to 0.14 mg per liter, or 1/10 of the lower explosive limit. This entails methane stripping from the leachate. The greatest environmental risks occur in the discharges from older sites constructed before modern engineering standards became mandatory, and also from sites in the developing world where modern standards have not been applied. There are also substantial risks from illegal sites and ad hoc sites used by organizations outside the law to dispose of waste materials. Leachate streams running directly into the aquatic environment have both an acute and chronic impact on the environment, which may be very severe and can severely diminish biodiversity and greatly reduce populations of sensitive species. Where toxic metals and organics are present, this can lead to chronic toxin accumulation in both local and far distant populations. Rivers impacted by leachate are often yellow in appearance and often support severe overgrowth of sewage fungus. Problems and failures. Leachate collection systems can experience many problems, including clogging with mud or silt. The clogging can be exacerbated by the growth of microorganisms in the conduit. The conditions in leachate collection systems are ideal for microorganisms to multiply. Chemical reactions in the leachate may also cause clogging through generation of solid residues. The chemical composition of leachate can weaken pipes' walls, which may fail. Other types of leachate. Leachate can also be produced from land that was contaminated by chemicals or toxic materials used in industrial activities such as factories, mines or storage sites. Composting sites in high rainfall also produce leachate. Leachate is also associated with stockpiled coal and with waste materials from metal or mining and other rock extraction processes, especially those in which sulfide-containing materials are exposed to air and thus to oxygen, generating acidic, sulfur-rich liquors, often with elevated metal concentrations. In the context of civil engineering, leachate refers to the effluent of pavement wash-off that permeates through the cement paste onto the surface of the steel reinforcement, thereby catalyzing its oxidation and degradation. Leachates can be genotoxic in nature. References: Henry, J. He G. Environmental Science and Engineering, Prentice Hall, ISBN 0-13-120650-8, DOE Report CWMO 39A+B/92 Young, A. Washington State Department of Ecology, Solid Waste Landfill Design Manual, Present and Long-Term Composition of MSW Landfill Leachate, a review. Peter Kjelsen, Morten A. Barlers, Alex P. Rooker, Anders Born, Anna Ledin, and Thomas H. Christensen, Hansard, The Deposit of Poisonous Wastes Act 1972, http, www.leachate.co. Arkan Introduction HTML. Christensen, T.H., Arkoshu, and Stegman, eds. Landfilling of Waste Leachate. London, Elsevier Applied Science, 1992. Print, Dictionary of Environmental Science and Technology, 3rd edition, Andrew Porteous, ISBN 0-471-63470-0, pg 25. Singer, Chandra S., Kumar-Gupta S., Chauhan Lake, Kumar-Rath S. Mutagenicity of leachates from industrial solid wastes using Salmonella reverse mutation assay. Ecotoxical Environs AF 2007 Fabe. 66, 210-6. EPUB April 18, 2006. External links: An Introduction to Leachate, Landfill Leachate, Free Access Leachate Aeration System Drafting Software for Diffusers, Solid Waste. Washington Department of Ecology.